This is video 2-2. It's to be watched Thursday, 9:30. And yesterday we talked about average rate of change over an interval. Today we're talking about the instantaneous rate of change at a certain point. So I'd like you to write down first this chart here that I have describing the two things and how they're different. Average rate of change on an interval is the slope of the secant line that intersects the graph at the endpoints of the interval. Instantaneous rate of change at a point is the slope of the tangent line that just touches the graph at that point. Notice the difference, guys. Secant line versus tangent line, that's a difference. But average rate of change is on an interval. Instantaneous rate of change is at a point. Okay. Homework for tonight is page 4 all. And let's just jump right into this. We're going to do 2 pages. So here I have a function. It's a parabola. I have my vertical axis labeled as W, and I have my horizontal axis labeled as R. So down here in the graph above, blank is a function of blank. Well, W is the output, R is the input, so W is a function of R. Okay, and I'm just going to go off to the side, and then I'm just going to write a little note to myself. So if this is true, if in the graph above W is a function of R, then we are dealing with the graph of W of R. Okay, and now we're going to estimate the slopes of the tangent lines at the following values of R. So I'm giving you a value of R. We're going to find the tangent line slope. These are rough estimates, guys. So, if you decide to break off from me and then look back at what I got, we might differ, but that's okay. Now, instead of drawing the tangent lines, what we're going to do is we're going to use this transparency that I gave you in class today. Okay, so we'll use that. I find that easier because you can fuss around with it till you get it right. So we're going to do R at R is 4. We're going to do the tangent line there. So I go to my graph. I find the point on the graph that corresponds to the input value, or in this case the R value 4, and then I take my transparency and I just line it up so I have a tangent line. And okay, now the first thing that's important to notice is that this graph, the inputs and the outputs are going up in increments of 2. So this what is that called? The scale maybe is 2. So yeah, when I'm counting rise over run, I have to keep that in mind. So let's see. Earlier when I did this, I got 6 over 5. All right, so let's see if I get that again. Okay, so I'm going to go, and it's important to find a nice point. This that we're starting at is a pretty nice point, and then I see another pretty nice point like there. Okay, because that's like a 0.5. It's not right on like an intersection point, of the boxes. It's not right on the corner of a box, but it's a 0.5, and this is going up by increments of 2, so that's not too bad. Okay, so I'm counting by 2s. So I've got 2, 4, okay, only 4. All right, so 2, maybe I should adjust this. 2, 4. Okay, so the rise I'm getting here, I'm writing it down below so I can remember it. The rise I'm getting is 4, 2, 4, and then I go left, 2, 3. Okay, so I'm getting 4 over negative 3. And okay, so I'm getting negative 1.3 repeating, which is a lot different than what I got when I was doing this earlier. When I was doing it earlier, I got negative 6 over 5, which is negative 2.2667. But that I'm not unhappy that happened, because this just highlights how rough these estimates really are. Okay? so there's that. Now, the next one, we're going to do the slope of the tangent line at 10. All right, so I go down here. Yeah, and guys, feel free to break away from me and get different estimates because, you know, this is not an exact thing that we're doing here. So there's the tangent line. This one, we should all get the same thing. The slope of that is a horizontal tangent. The slope of a horizontal line is 0. Okay, here we go. And now at 14, right there, when I did this the first time last night, I got 4 over 5, which is 0.8, but let's see what happens this time. Alrighty, so there's, and notice like the variation, like that looks tangent, you know, so that's why we can't really be super exact here. Once we are working with equations, we will be. But when you're estimating from a graph, it's not going to be pretty. Okay, so there we go. So I guess I'll count from here, and then I'll try to find a nice point. That looks like a 0.5, you know, vertically. So I'll say that this is about 2, about 3. Okay, so it's like I'm going up 3. About 2, 3, 2, 4, and then right 4. Okay, so this time I got 3 over 4. And I got 0.75 this time. Okay, guys, so now, and I'm doing this in the morning, so excuse my morning voice and my morning mind because I'm a little groggy. So number 3, what is the symbol for the slopes of the tangent lines to this graph in prime notation and Leibniz notation? All right, well, the name of this function is W of R. I just talked about that. So if we wanted to talk about the, if we wanted to use prime notation for the slopes of the tangent lines, it would go W prime of R. Okay, so this here would represent the slope of the tangent line at any given point R. And now let me go like this. Okay, so off to the side. This is just an aside. So for example, the first number, the first tangent slope that we got would have been, all right, so let's go over here and say examples, would have been W prime of 4. Then we found W prime of 10. And lastly, we found W prime of 14. And let's say over here what they equal. So here I got, I'll use the fractions. I got negative 4 over 3. Then I got 0. Then I got 3 over 4. All right? So there's that. There's another type of notation, which is called Leibniz notation, which is named after the guy who is credited with it. And Leibniz notation, guys, comes from the when this guy Leibniz, when he made up this notation, his influence was delta y over delta x. Okay, because that's really what we're finding. We're finding a slope. So we're finding the change in y over the change in x, or the change in output over the change in input of a tangent line. So let's go over here and go like this. And just write for ourselves that it came from delta, instead of y, we've got w over delta r, okay? But he just changed the deltas to d's. So we would say dy, or dw, over dr, okay? Now let's do some examples over here, how this notation would be used with what we've, with the stuff that we just found. So it would go like this. It'd go dw, dr, and then you do a bar, and then right down below I'm going to go r equals 4. Okay, so this would mean the instantaneous rate of change at the r value 4, and we found that and maybe they wouldn't even maybe they would just put a 4 down there instead of r equals. I'm sure they'd be fine too, because this is bothering me that I have two equal signs next to each other. Equals -4/3. Okay, so let me try it a different way. dw over dr, I'll just do one more, bar 10, and then we ended up with 0. Okay, the prime notation I prefer, but you'll see Leibniz a lot, and you'll definitely need to be able to recognize it and use it. Okay, guys, now flipping to the back, we've just got another one. I'll go a little bit faster here. So this time our vertical axis is C, our horizontal axis is S, and so therefore in the graph above, C is a function of S. Okay, so the function we're dealing with is C of S. Tangent slopes. Okay, at 8, all right, I went like this, and just to speed things up, guys, I'm just going to tell you what I got last night. Like, I'll show you the tangent line with the transparency, but then I'll just see what I got last night. So I went like this. Okay. And, you know, I counted the boxes. So you should try this on your own. But when I did this last night, I got 3.5 over 5. So as a decimal, I got, well, in negative, because this is decreasing, I got -0.7. So you should try that on your own and see what you get. Okay, but I'll just speed things up and go like that. And then at 14, okay, so I find 14, go up to the graph. Okay, take my transparency. All right, something like that. Okay, and last night I got 2 over 4, so I got 0.5 for that one. 0.5. It's an increasing tangent line, so it would be, you know, positive. And then at 24, this looks like it's going to be the steepest one, for sure. Okay, so there's my tangent line about there. And last night I got 4 over 2. I got 2 for that, which would make sense because it's definitely steeper than the others. Okay, in this case, the symbol for prime notation, our function is C of S, so it would be C prime of S. Okay, and over to the side, I'll just do one example. I'll do the second one. So for example, C prime of 14 we found was 0.5. Leibniz notation, remember it comes from the change in the output over the change in the input. So our output is C, our input is S, so it would be dC over ds. And let me do an example using the notation dC over ds bar, I'll again say at 14, and this equals 0.5. Yeah, it's better if you just put the number, I think. You could say S equals 14, that'd be fine, but I think it looks more elegant like this. Okay, guys, so that was a 13-minute video. So the homework is, I think I already said it, but let me reiterate, it's page 4 all, and I will see you later. Bye-bye.